Hi everybody, welcome back. This is unit chapter 11, lesson 5. I think it's lesson 5, and we're still on in our textbook section 4. Yesterday we dealt with non-volatile solutes in solvents, making a solution. Today we're going to deal with volatile solutes. So really there's a second part of Raoult's law, and it really deals with when the solute is volatile. You can recognize these problems because they'll always say something like, assume an ideal solution. Assume the solution is ideal. And I'll talk about why they say that in a minute. So actually in your notes, there's something that says non-ideal solutions. You should cross that off, okay? Because I don't know why that's really there, but it's misleading, I believe. So cross off where it says non-ideal solutions, okay? And let's deal with these ideal solutions. Is that all it says? Just says non-ideal?
And then so just a sentence after that.
What's the sentence?
Liquid solutions in which both components are volatile.
Okay, that is what we're doing. So this part of it deals with liquid solutions in which both components are volatile, but we don't call them non-ideal. We call them ideal. We assume they're ideal. Okay, so liquid solutions where both components are volatile. I want to have my notes in front of me too, which is what I was doing, and then I got distracted. Okay. So I guess maybe just remove the word non, right? From your notes, cross out the word non.
Removing the whole.
Okay. So what happens with this is we have a modified form of Raoult's law. And then we'll talk about the deviations in a minute. Okay, so this is the word we're getting rid of. Okay? Since both components evaporate and contribute to the vapor pressure, we have to sum those components. So the total pressure will be equal to the pressure of component A plus the pressure of component B. And the way we'll get the pressure of component A in the solution is by taking the mole fraction of A times the pure pressure of A, and adding to it the mole fraction of B and the pure vapor pressure of B. So everywhere there's pressure here, it's really vapor pressure, okay? So it's the vapor pressure of A plus the vapor pressure of B. And again, the way we get the vapor pressure of A in solution is it's the mole fraction of A times the vapor pressure of A when it's by itself. This is the pure vapor pressure, plus the mole fraction of B times the vapor pressure of B. And again, that's the pure vapor pressure of B when it's all by itself. And since both of them are going to contribute to the vapor pressure, you're going to add both components together. Okay, for example, here's an example, and then we'll talk about the theory behind this. A solution is prepared by mixing 5.81 grams of acetone. Acetone is the component in nail polish remover. You know it's volatile. If you leave the cap off, you can smell it. It evaporates easily, okay? And 11.9 grams of chloroform. Chloroform is the stuff in the old movies they would put on a rag and put on your face and it would knock you out. It's also very volatile. At 35 degrees, the solution has a total vapor pressure of 260 torr. Is this an ideal solution? The vapor pressure of pure acetone and pure chloroform are 345 and 293 respectively. Okay, a solution's prepared. Let's write down our numbers. We have 5.81 grams of acetone, and if they give us the molar mass, and we have 11.9 grams of chloroform. At 35 degrees, the pressure of the solution is 260 torr. Is this ideal? The vapor pressure of pure acetone is 345, and the vapor pressure of pure chloroform is 293. Okay, so let's calculate what the pressure should be of the solution. And again, is this an ideal solution? The fact that they're asking that question lends us to that modified form of Raoult's law, where the vapor pressure of the solution is going to equal the mole fraction of component A times the pure vapor pressure of A plus the mole fraction of B times the pure vapor pressure of B. Since we need mole fraction, we should get moles. So let's take our grams and get moles for each one of these. I'm going to erase that, even though I just did it. We'll use it later. So I'm going to convert my grams of acetone to moles by dividing by the formula mass, which is 58.1. Okay? So I'm going to take my 5.81 and divide it by 58.1, which is going to give me 0.1 moles of the acetone. And I'll do the same thing for my chloroform here. 1 mole of chloroform is 119.4, which also gives me, what do we have, 0.0997 moles of the chloroform. Okay? So now I can plug into that formula. And I know they gave us the vapor pressure of the solution here, but in order to determine if it's ideal, I'm going to have to calculate it given the information and then compare it to what they're witnessing. And that will tell us if it's ideal. So the vapor pressure of the solution equals the mole fraction of the acetone times the pure pressure of acetone plus the mole fraction of chloroform times the pure vapor pressure of chloroform. So let's get our mole fractions. The moles of acetone are 0.1 over the total moles, which are 0.1 plus 0.0997. And the pure vapor pressure of acetone when it's all by itself is 345. Okay? The mole fraction of chloroform is 0.0997 over the total, 0.1 plus 0.0997, times the pure vapor pressure of the chloroform, which is 293. Okay, so if I take 0.1 and divide it by 0.1 plus 0.0997, I get the mole fraction to be here, 0.501. And the mole fraction over here to be 0.499. Okay, so now I'll multiply this and then add those two values together, right? 0.501 times 345 gives me 172.845. And 0.499 times 293 gives me 146.207. And I just add those values together and I get the vapor pressure of the solution that we should observe. This is our theoretical that we're calculating, assuming they behave ideally. It comes out to be 319 torr. Okay? Now, the question asked, is this solution ideal? Most questions won't ask that. Most questions will just ask you to calculate the vapor pressure of the solution. If we go back and we look at the observed vapor pressure of this solution, oh man. The observed vapor pressure of the solution up here is 260. Uh-oh. So what we're actually seeing out of this solution is a lower vapor pressure than what we should have. Why? So this is what's called a negative deviation. What we're actually seeing is lower than what we calculated. We calculated it to be 319, and we're measuring the vapor pressure above the solution to be 260. Well, obviously not everything's evaporating that it should be, that we would expect. And the reason that it's not, so we can say, let's just kind of summarize, that this is not an ideal solution. And it's not an ideal solution because the vapor pressure of the solution we observe is much less than the vapor pressure of the solution we calculated. Right? We observed 260, we calculated 319. Because there's interactions between the solute and solvent. Because they're attracting each other and preventing, I'll say reducing, the evaporation. So when we assume an ideal solution, we assume there's very little interaction between the solute and solvent. Okay, but obviously if we're observing a lower vapor pressure than what we would expect, then they're holding each other in the liquid phase and preventing that evaporation or reducing that evaporation. So that is not an ideal solution, because ideally we wouldn't have this. Ideally, in an ideal solution, the components do not attract each other. They behave independently, as if the other one wasn't there. So you would really just add their vapor pressures together based on their mole fraction. But because we got a lower vapor pressure, that what we're seeing is a lower vapor pressure than what we should have, that indicates that there must be some type of interaction. And that is what we refer to as a negative deviation from Raoult's law. The most ideal solutions are those where the components are alike. And have little interaction with each other. And that's typically two hydrocarbons. Because nonpolar molecules have the weakest interactions. So if you have two large nonpolar molecules mixing in the liquid phase, they're most likely to behave more ideal than any other type of solution. And I think that's it for tonight. So don't forget to do those 3 problems out of homework number 3, I think it was. They are numbers 15, 45, and 47. And we'll come in tomorrow. We'll have our naming quiz, which we forgot about today or didn't have time for. We'll go over the homework, and then we'll head out for our field trip. If you didn't bring me the permission slip, please make sure you bring it to me. Have a great night, everybody. Bye-bye.